New method to gauge atmosphere's ability to clear methane. New research by UMBC's Glenn Wolfe and collaborators is shaping how scientists understand the fate of methane, a potent greenhouse gas, in Earth's atmosphere. Of the greenhouse gases, methane has the third greatest overall effect on climate after carbon dioxide and water vapor. And the longer it stays in the atmosphere, the more heat it traps. That's why it's essential for climate models to properly represent how long methane lasts before it's broken down. That happens when a methane molecule reacts with a hydroxyl radical, an oxygen atom bound to a hydrogen atom, represented as O, in a process called oxidation. Hydroxyl radicals also destroy other hazardous air pollutants. O is really the most central oxidizing agent in the lower atmosphere. It controls the lifetime of nearly every reactive gas, explains Wolfe, an assistant research professor at UMBC's Joint Center for Earth Systems Technology. However, globally, we don't have a way to directly measure O. More than that, it's well understood that current climate models struggle to accurately simulate O. With existing methods, scientists can infer O at a coarse scale, but there is scant information on the where, when, and why of variations in O. New research published in Proceedings of the National Academy of Sciences and led by Wolfe puts scientists on the path to changing that. Wolfe and colleagues have developed a unique way to infer how global O concentrations vary over time and in different regions. Better understanding of O levels can help scientists understand how much of the ups and downs in global methane levels are due to changing emissions, such as from oil and natural gas production or wetlands, versus being caused by changing levels of O. A flying laboratory. NASA satellites have been measuring atmospheric formaldehyde concentrations for over 15 years. Wolfe's new research relies on that data plus new observations collected during NASA's recent atmospheric tomography (ATOM) mission. ATOM has flown 4 around-the-world circuits, sampling air with the aid of a NASA research aircraft. This flying laboratory, as Wolfe describes it, collected data on atmospheric formaldehyde and O levels that illustrates a remarkably simple relationship between the two gases. This did not surprise the scientists, because formaldehyde is a major byproduct of methane oxidation, but this study provides the first concrete observation of the correlation between formaldehyde and O. The findings also showed that the formaldehyde concentrations the plane measured are consistent with those measured by the satellites. That will allow Wolfe's team and others to use existing satellite data to infer O levels throughout most of the atmosphere. So the airborne measurements give you a ground truth that relationship exists, Wolfe says, and the satellite measurements let you extend that relationship around the whole globe. Wolfe, however, is the first to acknowledge that the work to improve global models is far from done. The airplane measured O and formaldehyde levels over the open ocean, where the air chemistry is relatively simple. It would be more complicated over a forest, and even more so over a city. While the relationship the researchers determined provides a solid baseline, as most of Earth's air does, indeed, float above oceans, more work is needed to see how O levels differ in more complex environments. Potentially, different data from existing NASA satellites, such as those tracking emissions from urban areas or wildfires, could help. Wolfe hopes to keep refining this work, which he says is at the nexus of the chemistry and climate research communities. And they're very interested in getting O right. Getting it right. The current study did consider seasonal variations in O, by analyzing measurements taken in February and August. The seasonality is one aspect of this study that's important, Wolfe says, because the latitude where O is at its maximum moves around. Considering seasonal shifts in O concentrations, or even multi-year shifts caused by phenomena like El Niño and La Niña, could be one angle to explore when trying to improve global climate models. Looking further at O levels on a global scale using satellite data validated by airplane data could also help scientists refine their models. You can use the spatial variability and the seasonality to understand at the process level what's driving O, and then ask if the model gets that right or not, Wolfe says. The idea is to be able to poke at all these features, where we haven't really had any data to do that with before. This new research is one step in the journey to enhancing our understanding of the global climate, even as it is rapidly changing. more accurately understanding how, for example, cutting methane emissions would affect the climate and how quickly could even influence policy decisions. It's not perfect. It needs work, Wolf says. But the potential is there. Physicists create stable, strongly magnetized plasma jet in laboratory. When you peer into the night sky, much of what you see is plasma, a soupy amalgam of ultra-hot atomic particles. Studying plasma in the stars and various forms in outer space requires a telescope, but scientists can recreate it in the laboratory to examine it more closely. Now, a team of scientists led by physicists Lan Gao of the U.S. Department of Energy's DOE Princeton Plasma Physics Laboratory (PPPL) and Edison Liang of Rice University, has for the first time created a particular form of coherent and magnetized plasma jet that could deepen the understanding of the workings of much larger jets that stream from newborn stars and possibly black holes, stellar objects so massive that they trap light and warp both space and time. We are now creating stable, supersonic, and strongly magnetized plasma jets in a laboratory that might allow us to study astrophysical objects light years away, said astrophysicist Liang, co-author of the paper reporting the results in the Astrophysical Journal Letters. The team created the jets using the Omega Laser Facility at the University of Rochester's Laboratory for Laser Energetics (LLE). The researchers aim 20 of Omega's individual laser beams into a ring-shaped area on a plastic target. Each laser created a tiny puff of plasma. As the puffs expanded, they put pressure on the inner region of the ring. That pressure then squeezed out a plasma jet reaching over 4 mm in length and created a magnetic field that had a strength of over 100 Tesla. This is the first step in studying plasma jets in a laboratory, said Gao, who was the primary author of the paper. I'm excited because we not only created a jet. We also successfully used advanced diagnostics on Omega to confirm the jet's formation and characterize its properties. The diagnostic tools, developed with teams from LLE and the Massachusetts Institute of Technology (MIT), measured the jet's density, temperature, length, how well it stayed together as it grew through space, and the shape of the magnetic field around it. The measurements help scientists determine how the laboratory phenomena compare to jets in outer space. They also provide a baseline that scientists can tinker with to observe how the plasma behaves under different conditions. This is groundbreaking research because no other team has successfully launched a supersonic, narrowly beamed jet that carries such a strong magnetic field, extending to significant distances, said Liang. This is the first time that scientists have demonstrated that the magnetic field does not just wrap around the jet, but also extends parallel to the jet's axis, he said. The researchers hope to expand their research with larger laser facilities and investigate other types of phenomena. The next step involves seeing whether an external magnetic field could make the jet longer and more collimated, Gao said. We would also like to replicate the experiment using the National Ignition Facility at Lawrence Livermore National Laboratory, which has 192 laser beams, half of which could be used to create our plasma ring. It would have a larger radius and thus produce a longer jet than that produced using Omega. This process would help us figure out under which conditions the plasma jet is strongest. The team included scientists from PPPL, Rice, LLE, MIT, and the University of Chicago. The research was supported by the DOE's National Nuclear Security Administration, the National Science Foundation, and Los Alamos National Laboratory. Computer simulations were performed on the Extreme Science and Engineering Discovery Environment (XSEDE), a collaborative partnership of 19 institutions, and the Argonne Leadership Computing Facility, a DOE Office of Science user facility.